All right, I'm getting started if that's okay, because I think this is it. So cool. Hi everyone, welcome back. Last week we talked about the first machine learning bits, and now I'm going to talk about some other stuff some other terms that float around. I've used this one in 390 a bit, 370 a bit. Is this moving? Yes. Okay. Here's the standard. No, yes, maybe. Okay, cool. So last week we talked about machine learning, unsupervised versus supervised. We'll just keep going in that theme today. Classification versus regression. So classification, discrete values versus regression, a value that's somewhere along a line. Do we have data or do we have a model, right? That's sort of like the first question to ask. If I have oodles of data, machine learning, if I have a model that data is coming in for, do I really need machine learning? And then training and test samples, how you split that up. And so some of these are coming back, unsupervised, supervised. And we'll talk about mostly big data, machine learning, and artificial intelligence. These are like the three buzzwords that you'll hear, and how I think we end up using them, or how I think I view these things. It's not the same thing that might not be correct. So feel free to absolutely correct me, because I'm learning this with you, I'm staying just ahead of the curve here. So big data, heard of the big data part? Big data has a good working definition. You have a working definition. Okay, we'll come back to this in a sec. Machine learning is the thing that we talked about last week, which is essentially model-less, but something that models it for you from a large data set. So to arrive at certain preset either classifications or a regression model that you set it. And artificial intelligence is really like this stuff on steroids. That's it. Like that's as far as I know. Everybody, half the articles I see about AI turn out to be just machine learning in a wig. So it's like really a big difference. Honestly, I think the working definition that I have here is that machine learning you do on a set piece of data, and AI is just constantly learning and constantly getting new data. So it's sort of like an ongoing process rather than a beginning and an end kind of thing, where you start with a data set, you train on the data set, you have the finished data set, you finished classifications, for example. You say, okay, I'm going to test it. I'm opening the envelope, remember? Like you go like, all right, I kept a little bit behind and I'm testing it. Turns out there's two envelopes, so we have like a second envelope that as soon as we go like, oh yeah, it went great. And then we have a second envelope and like, let's see how you did on the second one as well. And that's the validation set. And so that's when you go like, all right, this works, moving on with my life. And AI is sort of something that constantly learns and constantly gives you back, here's my classification, like it constantly updates. So it's more of an ongoing process. That's my working definition of this so far. First one's big data. I always love Googling these things and to see what the first picture that comes up. This is it for big data. That's really elusive. It's really just like, there's a giant strainer, and we put everything that you shopped for this year in there. I mean, at least that's what it looks like. Lots of Target and sweatpants. So big data is kind of like, it's very easy to stick that into your proposal for whatever you're planning to do. So suppose you want to start a small business. Suppose you want to get money from a grant from the government. Honestly, if you don't drop the word big data somewhere, you're just missing out on cash. Because it's the kind of thing that, oh, this is going to be it. Everybody's read Forbes articles about the fact that this is going to be it. The Economist has a regular columns, but nobody knows what it actually is. So what is big data? What is our functioning definition? Oh, okay. All right. So for the longest time, it was like anything that doesn't fit on my little USB stick is big data, or something that makes my laptop crash. So I don't like that. I like to have like a working definition at least. So the best working definition I've seen so far is an amount or rate of data that traditional methods cannot cope with. Basically, I know statistics, or I can find somebody in this building that knows statistics, and a million data points they won't bat an eye at. A billion data points I won't bat an eye at, right? That's not something that I really have an issue with. I can collect a billion points and I feel fine. And I can fit a straight line through that because I'm an astronomer and I don't do higher order things. So that works great. I don't need big data for that. Is that big data? No. 50,000 points, million points, it all works roughly the same. It takes a little longer, but even a billion data points your laptop can deal with just fine. So what's big data? It's basically the point that my usual computer really can't deal with it anymore. The rate is such that it comes in a terabyte a night, and I really can't even with a dedicated server, I'm starting to really struggle. If I would say for galaxies, like 250,000 galaxies, I want to look at those. There's a classical example. You want to morphologically classify things. So it's literally like a picture comes by, you say it's this kind of thing, and then the next comes over. It takes you a few seconds if you're a trained classifier for each galaxy. So a good classifier can do 50,000 a week. Now, if you're now dealing with several billion, or say several million galaxies, that is an impossible task. The usual infrastructure, just sticking a grad student in front of a computer screen and saying, go, doesn't work anymore. So now we've hit a big data point. That means that if your tools get better, your point shifts, right? So even if your statistical tools gets better, your computer gets, the latest generation of computer will be better than last week's, right? So the point where my computer starts to melt moves into the future. It is sort of like it's a thing that I cannot, not quite grab, but it's a thing that right now I can't deal with. And so if I'm planning ahead, and who here has heard of Moore's Law? Moore's Law of computers. What they noticed was that when we designed the very first computers, you basically plug those manually in. But you could use those to design the circuit boards for the next one. And then you could, as soon as that all was just printed on a CPU, so a single chip, so instead of having to manually plug every single processor into every other single processor, you could just now print everything on a microchip. That meant that the next design could be made by the previous design computer. So the processor speed and the amount of storage literally doubles every 18 months. This has been true since 1960. So we're on this like flat curve, like it just doubles in logarithmic space. The y-axis is logarithmic. So if I can say, well, my project's 10 years in the future, I know current computers are here, 10 years, extrapolate Moore's law. You know what? That many terabytes, not an issue. I can literally buy it off the rack at Best Buy. It won't be a problem then. So sometimes it actually makes sense in a technological project to just wait for whatever consumer products is happening to catch up with you. So you can go like, great, now I can just buy a Best Buy. Don't have to buy a Best Buy computer. I can just literally buy it off the rack. So if I do that and go like, well, the data's coming in 10 years. There's nothing I can do with it about that, right? I know my telescope is on schedule, so 10 years from now, this much is how much I'm going to get. For example, the square kilometer array will do a petabyte a night. Now, a petabyte a night is something that you can barely store right now. You can barely store a petabyte. A petabyte a night is a data rate that will just literally saturate every data center on Earth. So you go, oh, okay, so different mode. We need to go to some kind of different mode. We need to process the data as it comes in. We can't do the usual astronomy thing, which is like we sit on our data and just have our grubby little fingers on them for the rest of eternity. It's like it comes in, we process it, we have the final product, and we throw the raw data away. This is something that makes people of my generation just my head hurt, because I'm like, no, you never throw the old data away. You never throw any data away. It's like, well, you can't do that anymore. So whenever you hit something like that, where I don't know, people with gray hair start to flinch, then you know that, okay, we're sort of in the big data era. We're sort of like our equipment has to upgrade methodology or approach or a fundamental okay. Yep. So other ways you can think of it like cannot be plotted easily, right? So if it really is impossible, it has so many dimensions that it's hard for me to even put it in like a corner plot where I plot everything against everything else. And it's very hard to get like a feel how many different dimensions there are. Good example is the census is pretty simple, right? There's not that many variables for a person, at least that we record. But you, for instance, take an ICU patient. They have a lot of information that's flowing out of them. So that's already getting to a point. It's like, how do I get the relevant part out? Because, there's lots of noise. There's lots of heartbeat information, but maybe you just want the frequency or the changes of frequency or something like that. So if it suddenly generates too much data, too much dimensional data to plot easily, then you can say, oh, I'm getting too big data. It changes too quickly. Now, that's an excellent example of the data rates examples that I gave, right? So the Vera Rubin Observatory, for example, will generate 1 terabyte a night of reduced data. So this is imaging data coming in. And so every 3 seconds, we have a new giant picture in a filter, and then you have to file it away. I cannot look at all of that. I can't even look at a subsample. So I need something that selects the interesting thing for me automatically, or mostly automatically. So that's where you get to a point. It's like, oh, I can't actually look at everything anymore. I have to put something in between. Like, and so these are the things that are being built. Something that searches specifically for stars blowing up. So it looks for that particular signature. And we use AI for that kind of thing. We use machine learning. So something that's been trained on similar data and then looks for similar things in this like flood of data as it comes by. It just picks it out for you. You cannot go look at everything afterwards. It's just, we simply don't live long enough. Also, you need to eat and sleep, right? There's no way you can do this. Now, there are some people that basically go, challenge accepted. And they have, for instance, visually classified all spectra in the Sloan Digital Sky Survey, so all 3 million spectra in there, which, okay, that's great. But it is the kind of thing that's like, well, that is kind of the limit of human endurance, so maybe we need some, if we can do a robot do 97% of the way, great, that frees up the rest of my life. Sounds great. So you do kind of get like this whole big, if you talk to computer scientists or honestly to any physicist that has a server of some kind, they will typically start their talk, behold my computer for it is mighty. They do kind of want to show off like how nice and shiny their new machine is. It doesn't really matter. At some point we all move to Google or Amazon and simply just use their GPU farms. Okay. We have 2 kinds of big data, so roughly speaking. So this is the nomenclature that comes from big data people or machine learning people. And that is that they talk about barns and lakes, and it took me a little while to figure out what they mean here. The barn is collected, stays there, and is pretty static right now. I mean, there was a collection phase, you stuck it all in the barn, now it's in the barn, and you can work on it, right? So that's kind of a machine learning. You can do a machine learning on that. You go like, this doesn't quite work. Think about it for a bit, use a different machine learning algorithm, but it's a static collection of data. It's a big collection of data often already, but it doesn't seem to move much. But lakes is literally like got it out, right? Out of a creek. Is something that is, here's the state of my data right now as of last Tuesday, and it's like, oh gosh, like last week was so last week, right? That's the idea that you should have. Like, so that needs something that constantly updates, so more AI kind of applications. So this is, if somebody starts talking about data barns and data lakes, now you know what they're talking about. A static collection of data that, you have some time to work on and that doesn't age out. Or you have something that basically, last week's poles is a great example. No, not important. So whatever you over the old data sets. Okay. So examples. Yeah. I love this one because I learned it from another physicist that, yes, they have the real-time voltage measurement of every transformer in Louisville. And it's still unclear if they're actually doing anything with it. But they have it. They're collecting it. It just, chugs in and chugs out, and there you go. So what kind of data is that? Is that a barn or is that a lake? Lake, right? Because who cares about last Friday's voltages? That won't explain today's outage. So, yeah, I mean, for historical purposes, we may have stuffed it on a server somewhere, but nobody cares. Transients. So these are things that blink in the sky. So TESS is the Transient Exoplanet Survey Satellite. Is basically a bunch of cameras in space that are just constantly taking pictures. And the LSST, or the Vera Rubin Observatory, takes in the entire sky every week. So take a digital picture of the entire sky every week, do it again, do it again, do it again for 10 years. So that's a lot of data. So that aggregates as well. But is that a barn or is that a lake kind of situation? Who votes lake? It's the kind of thing, yeah. So it is the kind of thing that you can data mine later. So it kind of just aggregates in a barn, you might want to think of it. But it's like, if you want to follow up that particular thing, you can't follow up last year's supernova. It has already faded away. So anything that is transient and you need to do something about now, so you need to select it now for your telescope. So suppose you're at a telescope to follow up, a smaller telescope. We have one here in Louisville. They do TESS follow-up. So it's the kind of thing where they see that you see an explosion with TESS, they kind of go, alert. So there's an alert broker. And so the term, you'll hear this, is a kind of AI thing, which is basically takes a data stream like that, strains it, and brokers out, like the money makers, like they broker out, like here's this kind, like here's the candidates for exploding stars, here's the candidate for transiting exoplanets, so they've been trained to do one thing and just strain that out of a data stream. It's like, here they are, because you can't look at the whole thing, but you kind of funneled it down to something that you were interested in and only has like 3% false positive or like 40% false positive. Maybe you're happy with that, right? You're like, yeah, we can deal with that, but not the whole data stream. Polling is another example. I just gave that. Social media, is that a stream or a lake? Only when you cash out of Facebook is it a barn, right? Stream. Sorry, I said stream or a lake, but I mean, is it a barn or a lake? So you have these things that constantly update. So part of the whole big data problem is the fact it ages out. It becomes obsolescent. Can we think of a physics example? I give astronomy examples, but can anybody here think of a physics example of a data lake? Think of a big experiment that produces loads of data every day, and that you have to filter out because you want to get to like just the ones that do this. So Atlas, for example, produces enormous amounts of direct detections. And they even have machine learning algorithms in between the layers just to make sure that they throw away gigantic amounts of their detections. Because like, yep, that's a muon. Don't need to store that because we don't have the storage capacity for that. It is very stressful. So imagine that so I come from more of a like, well, I went to the telescope and I, had my instrument and I took my photons and I collected my photons and I took my photons home and, until I published it, and then I stuck it in an archive. Like, to me, it's like completely antithetical that like, yeah, the raw data we'll just throw away. especially radio data is a thing where the raw data is little orders of magnitude above the final product. So you go like, well, it makes sense to just keep the final product, but you realize that you can't clean or improve your data reduction. You can't clean the data anymore because the raw data is gone. That information is poof. And we're doing that right now. A team that works on the telescope in South Africa, and they collect about every 3 months is a petabyte. So 3 months is doable, right? You can stick it on data tapes, and it's sort of okay. A petabyte worth of disks is nearly impossible to buy, but a petabyte worth of tapes, $1,000, I think. So that's doable for a budget. So we image it all out after the season. So we image it all out, and that's it. Then they overwrite the tapes, and I'm still not okay with that. But we're doing our best we can on the existing data. We clean it up as best we can, and then we hope that as we combine more data, that no underlying low-level noise doesn't pop up because we can't fix it in the previous epochs. That's what we now got to deal with. So start thinking differently, which is, yeah, you can't keep all the information. You may have thrown away the raw data that you took at the beginning of your PhD before you even publish your PhD. It's like, does not sit well with me, but you should get to feel comfortable with that kind of thing. All right. So machine learning, absolutely a buzzword, but it's stir to data pile. And so stir to data pile until you've got neat little piles, or it takes the same color everywhere. So it classifies properly, right? We talked about supervised and unsupervised. So with supervised, training, testing, verification. Unsupervised, training, then classifying, and then verification. So it's the kind of thing that it goes, well, I got neat piles. No idea what. So there are a couple of examples coming along. But we always need a training and a testing sample. That's the one that I talked about last week. And then often we end up not doing this, but I really recommend it to kind of even have like a third envelope. So you usually go through a couple of rounds of training, testing, training, testing, training, testing. And then at some point you go like, oh, great, it works great on the test sample. And then it's really good to have like that third envelope and go like, and how does it work on the data that I've never shown this thing? So you can actually do a last test, and that's the verification part. I think of it as like it has a fourth one, which is exploitation. I'm not so happy about the word, but it's kind of like this is where, all right, I'm going to date myself. Who here has seen South Park? Okay, good. Well, there's a bunch of gnomes in South Park, and they start with collect all the underwear. Step 2 is a little vague, and step 3 is profit. That's the thing, right? So here it's like, this is the profit part, right? So we do the step 1, we train and we test our thing, and we even verify it. Let's say that verification is step 2. But in the last part, profit is where it's like, yeah, now new data is coming in, and I keep classifying, and suddenly that whole thing doesn't take me a lot of time anymore. So this is sort of like, this is where it gets useful. So that's the use part. So one example is neural networks. So I don't have a Jupyter Notebook on these yet, partly because they are CPU intensive. So they wouldn't run terribly well on these little computers. And but what you do is you end up with so the inputs are a bunch of vectors, and so that's how we typically think about input and output, right? We have the inputs are really data points that are a vector. So they're a bunch of entries. So each patient is a heart rate, a glucose level, an age, God help me, a BMI, or just a length and a weight. Like you have all these little data points, and so everybody is one of those vectors. So all your data points is a single vector, and they go in, and then you have a bunch of matrices that basically multiply this by certain weights, and those weights, they've kind of readjusted themselves, right? So that's what the machine learning part is. You let it readjust the weights until it gets these different outputs. Where the outputs are simply here's a whole bunch of data, and here's a bunch of these hidden matrices, these hidden weights, and they output a one of two, sick, healthy, for example, right? So there's a output layer that is just a few classifications. Now this part is hidden, and there's not just one layer, there's often multiple layers. So I love the fact that it's like, yes, I did this with a neural network. And it's like, yes, the neural network was called Steve, and I paid him $7.50 an hour. So, that sometimes works, but honestly, this might be better. So, for example, this is a convolutional neural network, and hopefully I can show you some of that, where you start with images inputs, and you have these maps that turn it into, that convolve the image with something. There's an example of image processing in a Jupyter Notebook, which shows things like edge detection. There are particular math approaches that if you multiply it, it shows like, oh, this is sensitive to things that are round-shaped. This is sensitive to things that that have an edge. If I approach it from the left, edge from the right, edge from the top, edge from the bottom. There's something that's like, oh, that looks like a bar. So these are kind of like generalized features. And that's what these feature maps are, and they basically do the same a bunch of times, and then you step down. You basically average out over a whole section and say like, okay, what's the average out? Then you step down, and then you do it again and do it again until you have an output that basically goes cat or dog, right? So you can train this kind of thing on lots of different input images. These things are fairly generalized, and so Google has like a library of these feature mapping things, and we often in astronomy end up using these. These were trained on like everything that was in Google Images back in 2016 or something, right? So they just froze that out and go like, here, you can use this. And then you can keep training it, because you have a large data sample. You keep training it until you end up with your desired outputs. So this is kind of thing that is a supervised version of this. So you take that image and you map that particular, like you take the whole image, that's the data point, and you map it onto a node. And that node basically gives back this is zero, has zero circleness in it, or has one, it's just a perfect circle and nothing else. And then usually it's a weight in between. And so you get this whole weight map of different shapes and stuff. And so you start with an image, then that first layer is just as big as the images. And so this is where all the number crunching happens. And then you step down. You average out a whole bunch of those nodes. And so suddenly the problem becomes a lot smaller. And you can have convolution. So this is a convolution step. And you can have, it's called max pooling. It's basically a step down. Like it's kind of taking the resolution of an image and just binning it, like just lowering the resolution of an image. You go like, yeah, I can still see what's happening here, right? So I can still see that that's good enough. It's good enough for like a little computer screen rather than blow it up to poster size. And then you can keep doing that until you end up with something that is just yes or no. So it's really just a data reduction kind of thing. So you can have a supervised. I have lots of inputs and lots of output labels. And so if I've labeled data, great. That's the kind of stuff that Facebook craved, so that you tapped on your face. So at some point they knew that they had enough pictures of your face, and they can go you, not you, effectively. So that's a data set with classifications available. But most of the time, there is no classification available. They just end up with a bunch of different outputs. It was like, well, this is all the cat-shaped things, this is all dog-shaped things, but you have to put a label on afterwards. So that's what convolutional neural networks are. And so it is really critical that the first thing that you do, like we talked about last week, is it supervised in an unsupervised problem? Does my data set is there a training set available that is big enough with labels available that I can use? Or is that easy to generate? So I've got that, then I can train it supervised, and supervised means that it has a high probability of success, right? It's very good at the thing that you told it to do, but it's terrible at doing anything else. The unsupervised part is like, well, it's it's sorting things out in different piles, and it can find something new, which is, especially in science, something that we were interested in. But you know, the accuracy will be like, yeah, it's 75%. So, you know, you're missing 25. Can you live with that? So it's a bit of a, there's always a trade-off. If there isn't, you know, we've hidden it, the person that's trying to sell you something has hidden it very expertly. All right, so I did mention that there's different kinds, right? So you've got labeled data, not labeled data, and then, you know, are you trying to find, is it classification? Then we're ending up here. Is it clustering? That's classification without labels. Regression, that's a linear level. And then are you just trying to reduce the number of dimensions in your data? So this is the rule that they use for verification. So 60% training, 20% testing, and 20% verification. But it's also OK to do 70-30 and just do 70% training, 30% test. That's also pretty common. But I like the verification sample. If your sample is big enough to go like, well, I could verify this with like 20%, and then I can train this on 60, basically, then do that, right? It depends a little bit on the size. OK, unsupervised learning. The data is the training set. So there is no split, really. You don't need to split that because you verify afterwards. But the trick is to have a network that spans and resolves the features within the data. So you typically have, and I think I've mentioned the word hyperparameter before. So hyperparameter is basically the choices you have to make before you even train a single node or a single thing. How big of a feature space do I have? Like, which features do I pick to go into this? Like, which ones are useful and which ones are not? How big of a, so this is an example of a self-organizing map. So this is a thing where it's like how many, every machine learning algorithm has like a little knob that you can dial. Like how many nodes should I use? How big of a map should I give it? And you go like, well, as big as they go. And it's like, well, that takes longer because that will take the computer longer. So you always have to compromise somewhere. And so these are the choices you need to make up beforehand. And so there's also dampening the learning curve. Like this is something that happens all the way down in the algorithm. You can always feed it more data and have it treat it like it hasn't seen any data before. But you have to curb that enthusiasm at some point, right? Because otherwise it'll run around like a toddler in a toy store, right? It'll go over here to the Playmobil, there to the Legos, and now it's just all over Legos and nothing to do with Playmobil, right? So you need to dampen its enthusiasm over time. Basically, I'll illustrate in a bit, but there's a learning curve. You have to stop from learning 100%, like moving to the next data point. So you have to kind of, another good example is, I think, a bunch of 4-year-olds playing soccer. Have you ever seen that? It's a clump of 4-year-olds running around the ball. And there's no learning curve. So they'll just be a clump of 4-year-olds around the ball for the rest of the game. Or you can learn and go like, no, I don't have to follow the data around all the time. It actually makes sense to stay put. And so you need to start, separating yourself away from the data. And there is basically a curve for that, usually an exponential. So self-organizing maps. This is a thing that I like working with. So hey, that's our example. Also, your computers can deal with it easily. So you had your vector data going in, right? So you've got your input is multidimensional. So it's a vector of like, say, 5 things. It's one of those like things where you're like, if you're new at a company, they go like, tell us 5 things about you. Great, here are the 5 things, right? So everybody has 5 things that they had to put in. Like, here's my hobby and a half, and I like this food, and there you go. I'm this tall. So here you can got to go like CMYK coloring. So that's a bunch of values that's a vector. Like every color is a vector. What you can then do is initialize a self-organizing map. So you just, every point on this map is a vector of that dimension. Can you imagine that? Okay, so this is the part where I go to the whiteboard. and hope it doesn't break. Cool. So I have a map. So self-organizing maps are a way to reduce multidimensional parameters, so 5 things, right? We have our 5 things. Let's see, we have our 1, 2, 3, 4, 5, shoot, 6. Okay, fine, 6 things. We have our 6 things. That's our data. And so we see that every node here is one of those. Boop. That thing there is a 6-dimensional vector. And we have another 6-dimensional vector over here, another one over here, another one over here, right? So it's kind of like, think of it as a stacks of cards, right? Stacks of node cards, and there's 6 of them on each spot on the board. Okay? I'm seeing a little bit of nodding, so, and not this kind of nodding, so we're good. Okay, fine. So every node has been randomly seeded. Oh, yay, here's random again. Fantastic. This is why we love random. So we've randomly put a value in there, and so every node is a random example of what your data looks like. And if we're a little smart, we've whitened the data, and we basically given the nodes the same mean and standard deviation. But other than that, they're randomly seeded, right? So, so what we then do is we go through all the data. So we go like, all right, data point 1, here's data point 1. We go through the whole sum and go like, what's the closest point that we can find? What's the closest, in this sea of random values, what's the closest data to our data point? Alfred, our first data point, comes in and goes to come to teach our sum, right? So here's our first data point and goes, and we're here. Excellent. Now what do we then do? That node and some of the nodes around it get to learn from Alfred. Alfred, our first data point. So you can sort of split the difference, for example. So you go like, all right, all the values in here move closer to the data. Now that's true for here. Here we do like split the difference, like we go halfway. These that are nearby but not as close get to split like a quarter of the way towards Alfred. So they all take a step towards Alfred. So they all resemble Alfred after this interaction a little more. Okay, Alfred goes away. I need a name of the bee. That's not mine. Beatrix. Right, so Beatrix comes in, and that data point is sitting here. And it also teaches all those nodes. And then the next data point comes in, and the next data point comes in. And you keep doing that. However, over time, instead of taking like a halfway step, that learning curve goes like this. We started with like step 50%, like do a halfway step. But after umpteenth iterations, we only do like a third of a step, because then we only have to teach all the nodes a little bit, right? We have to nudge them a little bit closer. So you can go once through all the data, or you can go many times through all the data until basically you've dampened this out and it's learned. So now I've got, say, these things turned out to be people, right? So I've got a new student coming in. Charlie comes in, and there we go. And now we go in, so, and they end up, over here. And it turns out that everybody like Charlie also gets to that node. And everybody almost like Charlie ends up in the same corner. Right? So you end up with a landscape where you go like Charlie-like people and, Diana-like people. So you kind of end up with a landscape. Now, because it was randomly seeded at the beginning, if I run this again, even on the same data, these nodes could be ending up completely different places. So the instance that we trained it on, and this is a learning trick, right? This is not something I can keep doing. Well, no, it's not something I can keep doing. I've taught it on this data. So was handed a data set, I taught it on this data, I have this one instance, and it's good at classifying things, and it grouped things that are exactly alike, they sort of end up with the same nodes. So if there's like a thing that there's one example of, they end up with the same nodes if all goes well. See how that works? So this is an example of a unsupervised machine learning, because you end up with like a clump of nodes that are like greens and a clump of nodes that are like yellows. And they're over here and they're over there, and I only have to classify the nodes, because for each node I can go, give me the data point that resembles it the closest. Just let me show me that, right? And go like, oh yeah, that's a green, and that's a yellow. And so they end up in that corner, and they end up in that corner, and so, boop. That's what they did here. Essentially, sorting the colors. So you end up with yellows over there, greens over there, and so there's a couple of these colors like sky blue where would that end up? Here with this node, with this particular node. I do have to make a couple of decisions right up front, right? How big is this map? How many of those nodes do I put in there? 3? No, that's nowhere near enough. 1 million? Way too many. So I have to come up with like an intuition of like, this is about right. How long do I train this on? How big of a data set? Well, this is every color in the CMYK range. So this is every color that your monitor knows. And it, so it sticks them in, and it has enough information to do that. So good example is that you've got, like, here's all your random data, and it starts organizing them into, like, it goes through a bunch of learning points, so it keeps adding a new data point and then moving. So the shading that you're seeing is like, these are all the nodes that have learned from this data point, so they've moved a little closer to that data point. This is a different way of showing it. But you start with like a randomization, and then they keep moving in the direction of the nodes that the data point, that the latest blue point that you gave it to. And over time, you kind of see that the shading of the red moves closer to the data point. You're starting to not influence the whole map, but less and less local, more and more local. You squeeze it into a solution kind of thing. Can't do it immediately, because then you basically end up with a random again, but you sort of pull it in the right direction. This is the other way to visualize this. So I really like these things because it's unsupervised, and it allows me to, for instance, find a clump that I would have not known was there. And I'm secretly hoping that my feature space is rich enough to give me like, oh yeah, these are the things that I expected, and these are the things I expected. Oh, cool, there's a couple of weirdos right here, and I can get right to them. So it's good if you want to classify something where you're not quite sure, or there's maybe a gradient between one thing and another, and it's not exactly classifications yes, no, but yes, a little bit less, no. That's a good, this is good for that kind of stuff. So yeah, you get these visualizations where like every data point changes, and you get this hyperplane that you now, like, so 6-dimensional space we've now squished into a map, a 2-dimensional space that we can visualize. Yay, we're much better with 2-dimensional stuff. 3-dimensional stuff, I already told you that we're actually not great with. Like, just avoid 3D plots. I reiterate here, whatever you do in your thesis, as cool as it looks like, avoid 3D plots at all costs. All right, so you can condense your multiple dimensional data, and like you don't have to be restricted to 6, especially if you have like a very rich feature space. You kind of like, I don't know which one's important. That's also something that you can then test. You can look, which one of these features actually did I end up using, or is it sort of the same throughout, and there's like a little bit of weirdness, but it's like, yeah, that's actually not a useful feature. But if it's like, yeah, there's like this gradient across my map, it's like, okay, that's a feature that told you something. So you can actually go back and go, all right, which part of my feature space was useful to classify things with, and which ones were just noise? And so you can start throwing those out and do a new iteration with them. And so you can kind of winnow it down to like, this is the stuff that was important, and this wasn't. and you don't have to classify everything by hand. You have your computer do it for you. Okay? Cool. All right. So was that supervised or unsupervised? I have so many people in the room that I can do these things now, so it's good. What is this? Supervised or unsupervised learning? Okay, who is in favor of supervised learning? And who is in favor of unsupervised learning? Okay, yeah, this is unsupervised learning. Cool. So the settings, the hyperparameters, right? I haven't called them hyperparameters yet, but that's really what I think of it as settings. The choice of the map size, super important, because how much resolution do you want? How many nodes do you need in there? You can kind of feel that, 3 across and 3 lines, that's probably not going to do it, but it's kind of something that you have to guess at, because how many heaps do I expect in there? How far-reaching is each update? Like, so basically, if I plunk in a new data point, does it affect the entire map, or just the last few nodes? Or do I squeeze that over time? And how fast do I squeeze that over time? And so that dampening the learning, like dampening its enthusiasm, how do you do that? And is my data set big enough to do this at all, right? Is the feature space enough to discriminate between things? And do I have enough iterations of it? So if it's a few thousand, I'm like, I don't know. I've got 50,000. Yeah, that'll do. So, you need to figure out if you've got enough data to do this with to begin with. All right. Here's another example. K-means clustering. So this is sort of like the simplest. I love these little videos. So is this moving? Yes, cool. Initialization. So I've got a bunch of clumps. Data, 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 and data. And I'm putting random points down, but I said 4. So I had to pick 4 clumps. This was a choice that I made, right? This is not something the algorithm did. I said, yeah, 4, that'll do. Randomly put them in, move them closer. So it's going too fast a little bit, and you know what I'll do? Is it playing? Yes, so randomly placed down, and then I say, okay, which point are the closest between these two? These blue points are the closest to this blue node that I plunked down. The yellow ones are here. And then I move them to the mean point of the one that, like, I take the mean area of all the data values, and then I move my node there, and then I redo that. Did that go too fast? So what I do is you plunk down your data, your node, and you go, okay, which ones is it this, between these three, like this data point, where is it closest to? It's closest to that one. So it belongs to this node now. And then you end up with a whole bunch of data points that belong to this node. You take the mean here and the mean here, and that's where you place the node again. Then you reassign every point and recompute the mean. You keep doing that, and you end up with something that describes the data as like a bunch of groupings pretty well. It really works fantastic, especially considering this is just a, bespoke, custom-made example, of course, because real data doesn't work that way. But the first thing that you should notice is that he or she picked 4. If I had picked 3, we would have ended with 1 here, 1 here, and maybe 1 here, or something like 1, 2, 3, and this group was split down the middle. That wouldn't have described the data as well. So I think we talked about K-means clustering, but on Thursday, this is how you do it, right? You say, okay, I think there are 4 clusters in here. You can try this and go like, how much? Because now all these blue points are pretty close to this thing, right? And these are all pretty close to this yellow one. If I put 3 in here, like 1 here, 1 here, 1 here, then there's like half these points are far away from that blue point. So actually the sum of the distances between the node and all your data points becomes a lot higher, right? And it becomes unacceptably high. And so that's the elbow plot that I showed, where it's like, okay, well, what happens if I use one node? Well, it's sitting over here, and it has to go all the way out here. What happens if I do 2 nodes, like 1 here, and these are sort of split in between? What happens with 3 nodes? 1 here, 1 here, 1 here. This one's still unpleasantly split. 4 nodes suddenly go like, okay, there's now a significant drop that I don't have to cross space to get my next data point. So suddenly, like a noticeable drop. All my data points are nice and cozy to my mean. So now I think I have the right number of nodes. So you basically. So this is super useful if clumps are, well behaved like that. Sort of round spread. There's nothing too elongated here. This is sort of already at the level, and then yeah, they're nice and cozy to their mean nodes, and then yes.
The real data set, say there's 7 arbitrary clusters that we don't know about.
Yeah.
This still seems useful, but is there a more efficient way to find those clusters, set a different test?
So we can use self-organizing maps in that case. If you don't know how many nodes there are, or if they are a weird shape, or is this the feature space that I wanted to begin with anyway? So if you have less intuition of how much there should be, and so both about the features that you should feed it and the number of nodes that you expect there, then you kind of move away from k-means. K-means is super easy for a computer to do because computing the mean out of a bunch of data points, it's great at that. So yeah, it takes. The first time I ran it, it was like, all right, well, I'm going to run machine learning. I've got time for a coffee break, so click, and it's like, oh, it's done. So it takes no time at all. So it's a really neat thing to go build some intuition with. It's a good way to see, like, okay, how good are these things separating out, really? And so instead of doing like a fake data set like this, I'm giving you a real data set because that's the kind of physicist I am, right? We're giving you real data that I've worked with, so I know pretty well. It is relatively small. It's only 7,000 points. So it's kind of thing that's like, I'm not sure if I can really train something on there. There's just not enough data, maybe. But this is wonderful for just like, oh, well, there's, X clumps. How many clumps are there? And that's something that you can probably answer with that. So I'm writing this up now. So we originally did a paper back in 2019 that used k-means clustering on this data sample. And it's like, yeah, there's about, we did this. How many clusters were there? And you said 2, and I said 3, and we sort of agreed that it was somewhere between 2 and 3, really, because that's another problem. You need unit numbers of clusters. Something like self-organizing maps is perfectly happy with a cluster and a half. Like there's a clump here, clump there, and there's stuff in between. So you can have some subtlety here. Here it's like, yeah, it's either this or that. So it's very either or. That can be fine. And so there's a data set. That's the data set that we published first. And so you can play with that. You can see how well it does. And you can squint at it and see how convinced you are by this. So that's what was last Thursday's exercise. But I'm now running it through a self-organizing map to see how well that actually separates out. And you start to see that there's like spurs and like, yeah, this doesn't actually, they're not neat clumps. They're real data. So as soon as you work with real data, be aware that every machine learning algorithm has its limitations. This one is, it's either a blue or a yellow. There's no in between. It's almost like a football club. So this is just not work. Like that works great on this data. Work maybe on real data. Maybe it does, right? So people, this is a good example. Target audiences. Target is like one of those companies that has embraced big data in a huge way. Maybe you haven't noticed it, but you have a target card. I have a target card. We all have a target card, right? So we all have our customer shopping card. and it will figure out where we live and which target I go to. This is the kind of example of figuring out whether or not you should build an extra target. These people go to this target. These people go to mostly this target. These people go to this target. These people go to this target, this target. Maybe I should put one here, because all my customers aren't here. There's a hole here. Unless that's a forest, I should probably put a target there. So it is. It was like, yeah, that has a very much a, you're either going to that one or not that one. I don't shop at more than one. Let's put it that way. So maybe that works. This will do. But maybe I'm in a dense environment, New York City. These are the 6 boroughs of targets. Actually, yeah, there's lots of people that go to like 2, depending on whether they just come from work or it's near, or they're starting at home, right? So that's when it gets gnarly, and it's like, oh yeah, my neat little flatland space has suddenly just warped because it's super easy to go to that target or that target, depending on if it's on a metro line, or for example. So then it doesn't matter, and people end up going 50% to either one. So it's like, yeah, this cute little thing doesn't work anymore. I need to do something more intelligent. So usually we start here and go, will that do? Yeah. And then you could have something more, smarter way of classifying these things later. This takes no time at all. So this is good to build intuition. Again, was this supervised or unsupervised? Was this supervised? All right. Is it playing? Nope. We should actually, they have an ouverture or something, some music playing. So as soon as I plunk down these things, do I have any labels? These things have no labels. It's giving these labels because I randomly seeded those nodes, but it didn't have the labels to begin with. And do I change the labels? Yes, these things move to their centers and then relabel everything. The data had no labels to begin with. So this is, the nodes do the labeling. So you say there are four nodes, right? Here I am going, there's 4 nodes. There are 4 nodes, right? So that's the only labels I've got. Like, there has to be 4 categories. There isn't a thing where I said this is where they're supposed to be, or the data belongs to this node, right? As long as the data doesn't have a label. So supervised or unsupervised, did I start off with data that had a label? No. I just said there must be 4 kinds of labels. So that's unsupervised. So if I know how many flavors of ice cream, that's unsupervised. If I get a shipment with labels on the side, that's supervised. Kind of come up with that on the spot. I'm quite proud of that. So, okay, so the subtle difference in output that so it's the thing that you're after, right? So what am I after? Do I want to get really good at finding X every time? Be really reliable. I don't care about everything else. The 3% could be like, and stuff. I don't care. So for example, I am a supernova hunter. I'm interested in supernova of a very particular flavor. So I want to be really good at finding those. What about really, unique supernova? Don't care. I want those, right? So you're think the 3-year-old in the ice cream shop. The blue Smurf flavor, right? Everything else could have like 500 different flavors. Doesn't matter. 97% of the time, blue Smurf. So that's supervised. That's where that excels at. At the thing that you already knew. Your customer knows exactly what they want. Now, unsupervised, I have no idea. I have 2 of these, so one of them would come in blue Smurf and ready to leave already, and the other person would come in and go like, well, what do I feel like today? How many different flavors do you have? Let's go ask every possible permutation of all the 20 flavors in there. We were there a while. So I have no idea what there is, but I want to know how many options there are. So that's a different question. So parse out what your question is. We talked about this on last week, whether or not you should use machine learning at all. If you go like, I have a model, I have data, I know what, like that's fitting. do that. Don't use machine learning. But it's like I have data. I am being asked to filter this particular thing out. Oh, cool, I need to do this. I'm being asked how many of each kind there is in this data. I should be probably closer to that. So it depends, because if this is your goal, it's worth labeling a ton of data yourself, like to go through them and basically give it a label. And at some point, you become a expert classifier, and you have expertly classified data, and then you can basically reproduce that. That's all you wanted. But if you go like, how many kinds are there? I want to explore my data. I'm not exactly sure what I want, but I want different piles of it. That's where unsupervised comes in. All right, third buzzword, easily the most hyped buzzword, AI. Honestly, I have no idea what we're doing with it, other than it's basically machine learning with a hat. And so the other thing is there are non-standard difficulty settings. Now, this is sort of a thing where this will happen, where a professor will come. You are working with a professor, and the professor will be a machine learning kind of thing. Why? Because they just read an article that machine learning was going to solve all our problems, and they really have no idea whether or not this is a machine kind of learning problem. So I like this particular one where it's like a user takes a photo, the app should check whether or not they're in a national park. Sure, easy. It's a GIS, which is a geological information lookup. That is the kind of stuff that's already in the metadata of the photo. It's really like compare this position to a polygon example of longitude and latitude. Are you within or without? That is a solved problem, easy as pie. And the same thing, and check whether or not the photo is of a bird. So the questions are just as easy, yet one of them is a hard thing to do. Now you have to train on every kind of bird, whether or not, what it looks like in every kind of photo setting. That's a different problem than whether or not you have your geolocation. We have this in our feature data. I have no idea if this is in our feature data, right? So these things, you will run into something like, oh, this might be an unsolvable problem or a hard problem, and it's hard to tell from the onset. I'm running into headfirst at the moment in my research, so it's fun. And it all comes down to like, is my training set actually, does that have that information really in there? And this is why things like if you do run unsupervised learning, and then you get like a feature map, like a weight map, and you realize that one feature has like equal weighting across the entire self-organizing map, it didn't contribute. It is equally weighed for whatever node. But if there's like a nice gradient, it goes like, okay, so that feature tells you where you should be on the node. It's doing a lot of the heavy lifting classifying. So that's the one that I should keep, and the one that's flat I should just toss. Okay, so figuring out what your training set should be. This is a two-way thing. Don't keep cooking because you don't like the answer. Keep cooking because you think you can improve the feature space. Keep cooking because you think like, well, maybe the hyperparameter I need to adjust a little bit, but just going like, oh well, I used half the data because that's where the answer came out that we liked. No. So there is a judicious moment for you to go, here's the point to stop. I can overtrain, I can undertrain. These are you can overfit and you can underfit, right? These things are both true. Okay, so let's see, how am I doing for time? That seems about right, because I can talk for about an hour before I lose my voice. So today, I just wanted to go over these three things, and I wanted to explain what K-means clustering and what self-organizing maps were. These are the first two machine learning-y kind of Jupyter notebooks that I put in Blackboard, and is one about support vector machines, but we'll start on that. So I think we're up to assignment 15. So we're getting, if you keep answering the best you can, keep following on Thursdays that I just do a walkthrough. it's okay to just grab that, video and literally walk through. And that's the way you answer. Okay, so what does it mean? Because that's really what I want you to think about. Like, what kind of a classification is this? Does this work, right? I want you to evaluate whether or not the k-means clustering is the right way to do things here, or if a self-organizing map gives you more information or reduces it better. Okay, so thanks for coming. I will see you on Thursday. If there are now no questions. Questions. Yes, please. No? Yes? It is much. I'm sorry, everybody got slumps.